Mr. Balaji. He worked in Singapore and Australia as a technical consultant for about 2 years. In India, he worked as an assistant professor in the Department of Aeronautical Engineering for Hindustan University about 4 years and as an instructional designer for 3 years in India. He has completed dual masters in India and Singapore. In Singapore, he has done his Master of Science in Precision Engineering with specialization additive manufacturing and also Master of Engineering in Aeronautical Engineering. He has published 8 Indian patents in mechanical, aerospace and manufacturing.
Welcome to UGC lecture series on additive manufacturing. In this session we are going to discuss about stereolithography process, modalities and variants, and then the process parameter associated with stereolithography. First we would like to go with process and how the SLA can be processing and all those parameters associated with that. First we can see initially, like all additive manufacturing process, this also start with normal CAD diagram, and then the CAD input has been converted into SLA, STL files, and then that parameters has been given to the control unit. Control unit here we can see it's a laser and associated equipments related to scanning the particular material. Here we can see the basic equipments related to that. We can have a liquid polymer which in a tank, and a elevator platform which is going to move up and down depends upon the input given by our main parametric system, say for example from STL file, and then the base which is going to support the entire structure, and you can see the model is being printed over a particular resin tank. So this is a basic principle associated with this. Once the polymer has been kept in a tank and then the related input has been given to that, so that the monomer is converting into polymer, or we can say the process of polymerization done with help of UV lights. Okay, here mostly we are using UV related lasers because some of the lasers have its own advantages and disadvantages based on that. Sometimes we cannot use particular laser for particular type of polymer conversion because here we are not using it for the purpose of eating the material. That is a major thing by compare with other SLS or other additive manufacturing process. Here we are focusing particularly on only the conversion takes place. It's almost like a chemical reaction. That is a major difference between other methods and this one. Here we are converting the monomers which is being kept in a vat or a tank, that is being processed or converting into the cross-linked polymers, or we can say it as polymerization process. So that we can achieve with help of a laser input. So that is a major difference between other AM process and this one. And then we can have different modes or methods based on that, or we can call it as different modalities. Okay, what are all the modalities based on that? We can have the two base difference based on the SLA method. One is free surface method and fixed surface mode. Okay, what is the basic difference between these two? How this can be associated? See, for example, it's a free surface method. From the name itself, it is very clearly stating that the surface is exposed to air, or the surface is free to other atmospheric conditions, right? So that's why we call this one as a free surface method. Once the input is given from the CAD file, slowly the process takes place. Once the input as given and moving the particularly the top layer, you can see that's a pickup unit, and you can see in the zoomed view as well. That is the one going to control the entire motion based on that. Okay, you can see in the zoomed view. So this is a small pickup unit which is present in the exactly at the where the base is attached by the scanner. It's going to move based on that. We can have different control units, and based on that the motion is going to be done. But here, as we discussed in the last session, we can have the movement either in XY direction or XY or YZ or something we can alter, but it's very specifically based on the input given by the STL file. Some of the advantages compared to particularly SLS is here we can achieve both XY direction and opposite way, that is forward motion and backward motion, that is XY direction and YX direction. So both we can control easily while compared to SLS. That's a we can say that is advantages over SLS. What is the problem if we done same in SLS? If you think, what might be the problem if we did the same process in SLS as well? over curing. Okay, any other problem do you feel? Particularly while we can see some of the, I think one of your friend has been discussed about the curling effect, right? And what will happen if once a process is done in the same direction and in the reverse direction, particularly haze, heat affected zone, and there may be easily chances of getting embedded. One layer can be easily embedded if you go in the another direction. That's why they are trying to overcome with the help of adjusting the parameters of layer thickness as well as the intensity of the laser beam. But here the advantage of this one is it's almost in a liquid state. It is not exactly getting heated up. There is a process of addition of heat in this one as well, but it is only a chemical reaction change is going to be takes place here at the SLA. So that's why we can easily adjust the directions, because only we are going to have a chemical reaction that is based on polymeric conversion, that is from monomer to polymer conversion, not much about entirely the sintering or the heat input to the material. So that is a basic difference here compared to SLS. That's why we can have this one very conveniently in different environment, and as well as if you go for a fixed environment, we can get a quality product compared to SLS methods, because there may be very less chances of getting dust or any other contamination into it. Okay, that's a basic difference compared to SLA method. So here it's a free form. From that you can easily understand what is the process is going to take place here. Just only the input in the top of the layer, it is going to convert. You can see the top of the layer, once the input is given, it is going to convert into a solid state. That's it. Here we keep it all the material in a liquid state. So we can call it as monomers, or we can say some they are mentioning it as particularly monomers because it doesn't have any cross links inside. I think you might have understand the difference between monomer and polymer here. We can have a number of cross links between a structure that we call it as polymers, but sometimes they are mentioning it as monomers. I don't know what is the basic reason in it. Sometimes they are mentioning it as wad polymers, polymerization or polymer resins. So mostly from my understanding, all of the process it is converting from monomer to polymer. That is a basic process is being done here. This process is done in a free surface, so we call it as free form method. Okay, next one is this is done, it's a fixed plate. It's almost act like a normal, you can see the photocopier machine, right? It's almost work in that same principle. Here you can see the elevator is going to move upward. There you can see the elevator is going downward. That is, the elevator is going to merge inside the liquid. Here it is moving outside of it. Okay, you can see this base that is almost fixed, it never move. In that sense, only we can have horizontal line, that is XY direction movement only we can have. We don't have any Z direction movement particularly. That's why we call this method as fixed surface mode. And the elevator is going to move upward. You can see the final component formed, which is totally out of the fixer region in the bottom. So how this is achieved, particularly the laser input is given from the bottom side. You can see the two arrows, it's like focusing in this point, right? So this is how the laser is going to give an input. You can imagine almost like a photocopier machine. Once you can see the one movement of the slider is there, it's like a, you can see the light is focusing on it. So similar kind of thing once the input is given from the bottom, so that the polymerization takes place. Can you understand the basic difference between those two? Once the layer is formed, obviously based on the input we are giving from the STL file, it is going to move up. Okay, so these are basic methods, are two different modes how the SLA can be achieved. And the next one, we can have different variants. What is a variance? How the method can be achieved by some of the equipment change, or how the additional equipments can given to the system so that we can achieve the same process. So that is a system, we can call it as variance. What are all the variants we can have? This one we can call it as the scanning one, normal one, which we are frequently using for all other methods. And the second one, you can see this is projection based. So what's the basic difference between these two? Say for example, once the input is given, its normal head is moving, it's moving here. So you can see the normal process of polymerization takes place on each and every level. So once it is done, it is going to move down. But here they are projecting using a mask. What is the advantage of using, for example, if I am instead of laying up by layer, here also I am going to lay up by layer, but all in a single shot. Say for example, this entire mask is going to replace exactly the same size or shape, whatever maybe the mask is given based on the projection. So it is going to lay up the entire unit. So what is the advantage, do you think? What might be the advantage?
At the same time, same exposure will be there.
Okay, first exactly the better answer exactly. So you can see the exposure level are, we can have only embedded effect or curl effect only at the edges at the worst case, right? If you really focus a mask at a particular place exactly, we can avoid the entire curling effect or embedding effect. But what might be the disadvantage or what might be the problem, do you think? Say for example, if it is layer by layer, you can easily move the scanner, but you need to dynamically change this mask. Changing the mask may take time, depends upon the component, right? Say for example, I am just making a square. For that, I don't want to change the mask each and every time. Just the mask is going to be the same. But sometime what I will do, I may have n number of shapes. I cannot define this is the only product I am going to make using the SLA. So what might be the problem? I need to dynamically need to change this upper mask. Can you understand the difference? So that may take time, but another problem is that may sometimes having minor errors or minor problem with the component manufacturing itself. Say for example, if the focus is exactly done, we can get the perfect product. If there is very minor change, that may leads to product imperfection. So the minimum level at least. Can you understand the difference between these two? So what are all the parameters associated with SLA? These are all the 4 basic parameters. Mostly first parameter we can say that is CAD file or CAD conversion. That is a common problem in all additive manufacturing process. So that's why I didn't mention that one here. But these 4 are very important, particularly associated with SLA. Particularly what kind of problem they are facing in AM, particularly conversion of STL file is, in STL file their layer we are particularly concentrating on XY direction. Most of the segment they are making based on the XY direction. As we discussed, even the problem with AM, we cannot achieve the 100% accuracy in Z direction. So that's why they are converting to another file format, which is converting as a solid base. It considers a 3-dimensional solid, but input is given based on 3 layers. They call it as STC file, but still they got another problem while converting even that. So that's why still they are following up with the same STL file format. Because while converting, if you can easily imagine what might be the problem. Say for example, I am layering up based on XY direction, I cannot identify what might be the property or what might be the problem associated with Z direction. So that's very simple way. Instead, I can consider it as a global, as a full view of XY Z direction, and I am making it as a slice or based on layers. So that is easier for us to achieve the 100% accuracy. So, but they are facing a problem of, if they are considering on 3 axes, the machine is going to work only in 1 axis. That's a major problem they face. So they are not using that method of conversion, STC they call it as. That's why I didn't mention that one, because it's not only the problem for SLA method, it's common for all additive manufacturing conversion. So now they are trying to figure out with some other alternative file conversion method to achieve that process. It's very specifically we are discussing here about the SLA process parameters. One is irradiance and exposure. What is irradiance? Irradiance is very simple here. It's what is the radiant power input given to the unit area. So that we call it as irradiance. Here it is not going to give 100% heat, here going to give only conversion to the cross-linked polymers. Okay, so monomer is going to convert into cross-linked polymers. So what are all the basic laws or principle associated behind this one is, they have, I think you would have heard this principle, Beer-Allenbert's law. Beer-Allenbert's law is very simple. It's just in a very literal or colloquial manner, you can consider it as, once the amount of light is passed through any chemical or liquid form, how it is going to absorb, or it's going to radiate, or whatever the conversion is going to happen within the liquid state. That is being defined using Beer-Allenberg's law. So that's very simple. Why they are using here is mostly the irradiance and exposure is based on that, because once we are passing a UV light, right, UV laser input, what it is going to do, it is going to convert into the polymeric state. So how this association or how this process is going to be done. So what they are, how they are converting it is, each and every point the input is given. So they are considering a normal Beer-Allenberg's law, it is going to state how it is going to affect that particular polymer or how it is going to enhance the process. So they are having a fixed definitions and procedures. So it's like very open. You don't want to like keep on deriving so many steps or something like that. So it's very simple. It's straight away if you give the input of so much, say for example in terms of time or in terms of radiant power, how it is going to convert it. That is a simple process. So irradiance is simply its conversion from one state to another state. That's it. So exposure is again how much energy is going to taken in per unit area. I may give the input of, say for example, more than 1000 kilowatt or 5000 kilowatts, but the particular material has a capability to absorb that energy, right? Energy we cannot keep on giving to the material and it's not going to absorb all the material, or it's not going to convert the entire process until we get the final exposure, right? Say for example, what is a final exposure or what is a final limit here is conversion from one state to another state, monomer state to polymer state, or we can say it as liquid state to solid state by having the complex cross-linked polymer state. So how much energy is required, that is how we need to calculate. So once you are going to design a particular SLA device, if you consider these 4 or 5 parameters, that is if you optimize these parameters based on our needs to achieve a final product. Okay, so here the 2 parameters basically irradiance and exposure. Understanding the basic is like irradiance is just going to have a conversion from one state to another state, and exposure is how much energy is going to absorb by each and every molecule present in it. And the next one is how this laser and resin interaction is going to take place. What are all the problems may occur while giving the input of so much of power to that particular layer of a monomeric unit, right? What might be the problem, or how it is going to optimize, or how we can work with the laser resin interaction to achieve a polymeric state. So that we are going to discuss here. And here it's very simple. The line width is proportional to the part size. What is a line width is entire thickness of a beam, right? It is going to embed on a surface, right? So what is a input line, which you can very well understand the basic idea behind the light focusing. Once it is entered to the liquid, what might be the problem? In the center of the beam it have higher level of exposure that you might have came across many other processing event. So there may be possibilities of forming a parabolic shape instead of exact round or a square shape. It is going to make only the parabolic shape, but compared to layering a principle, it's very minimum thickness, so they are neglecting and they are forming it as they are considering it as a uniform thickness throughout the process. But in real fact, mostly it never produce exactly the beam shape input to the entire conversion area, that is the depth of cure, or we can call it as cure depth. Till that entire region, it won't be for sure it won't be 100% exactly the round or square shape, whatever it may be. What mostly it will produce almost a parabolic shape, right? But the parabolic thickness at the bottom is very less, considerably negligible, so they are still following the same process. But mostly the beam, once it is entered through the liquid surface, only at the middle, at the center, we can have the maximum exposure, right? So that's why it is directly proportional. Once the line width is directly proportional to the beam spot size, you can vary with the thickness of it, that you can easily achieve. Laser thickness you can adjust based on the output lens, or you can have so many lenses meanwhile to achieve even. It is like a vice versa process. Once the curing depth is again proportional to the line width, okay, because once the spot is entering, that is going to cure the entire polymeric chain. So it may not have the entire input is not going to segregate, or there may be any dispersion in it. We need to design a system according to that. That's also one of the parameter associated with it. If what will happen if once it is entered and there is some dispersion, sure there may be a considerable loss in it. So already we are using it for a very minimum time. I'll just in another slides I'll show you the time, how much time we are going to give the exposure it. So we cannot play around with varying the laser input or output. So for example, we need 100%, say for example only for 10 milliseconds, it should be 10 milliseconds, and as well the exposure time and the input power supposed to be 100% same for all the layers, right? So that's why these two parameters are very critical while compared to interaction. Once entered, automatically it should cure the required depth. That's it. Next is photo speed, or we can call generally the scanning velocity. Here we call it as photo speed. It's very direct again. Say for example, if you are varying the scanning speed, obviously it will vary the curing depth. That's a open. Say for example, if I need 100% same velocity input, obviously I am going to get the same curing depth. Even there may be some problem with the material, in that case sure there may be some difference, but considering the material is uniform throughout and the process is going to be takes place in a constant velocity, then we can say there won't be much difference in the curing depth. So you need to set, or we need to take care of it till all the process the velocity remains constant for the entire process. As we discussed even in SLS, once there is a variation in the velocity, for sure there may be different conversion rate, or we can say it's different formation of a curing depth or material conversion at a different places, so that we should avoid it. Even we discuss about fluctuation, so that is quite common. Whatever may be, we should have common same velocity throughout the process, then only we can able to achieve the quality product, right? So particularly this mostly even much sensitive than metallic products. Do you know the difference, right? Because it's almost in a liquid state. Even minor change may cause too much of polymerization, that may leads to thin the layers. It's going to may have thick the layer based on input laser. So even we should be much cautious than metallic conditions. Here we should have 100% try to have same velocity input. Again here this is the parameter mostly I like to discuss more, because it's based on the time scale how we are going to expose, that is going to make lot of difference in a product development, right? This is because mostly SLA they are going to use for a final products. We are not going to use for a prototypes, mostly we are going to use for a final product. What is the difference do you feel between SLA and SL? Mostly we are mentioning it as SLA. Do you know what is the difference? Why we are mentioning it as SLA or SL, or nowadays it's become frequently we are using SL? Do you identify any difference in between these two short forms, SL or SLA? Actually SLA is stereolithography apparatus. That is the one they given at the initial stage. Now while keep on they are using, even for normal stereolithography they are using this short form it as SLA, but it indirectly represent stereolithography apparatus. So why we are focusing apparatus more with associated with the time? Because here the parameter is going to give minor changes that will leads to major conversion rate change. So that's why you can see, that's why I want to mention very clearly here about the time which is going to expose it, right? One layer of photon from the laser it's entered, it is going to be only for picoseconds, not more than that. So think how we should be effective while giving the inputs. Even if you give more than a second, that is going to give a entirely a different product which we are not particularly required, right? So here if it is picosecond, we prefer to have a picosecond laser or femtosecond laser to have a exact time period, right? Picosecond time period. So that's why I just want to have, always you need to merge apparatus while talking about stereolithography. That's why they even, I don't know, that might be the reason to left over it as a SLA always instead of SL. But stereolithography short form is SL, but stereolithography now they are using it as SLA because they are always associating apparatus with that. You can see the generation of free radicals and cations, that is also going to take place within a picosecond time period. How effective we should be in exposing a laser, that we should be very cautious, because all is not even going to take place in seconds, right? So even exposure time, you can see it is only in microseconds, almost like it's in second. Again you can see the scanning speed, that's also in millimeter per second, right? That's also very minimum time period is going to use. So total process, even you can say the layer build up time not more than 10 seconds. That depends upon the material length again, but the maximum, the length which we have at the moment, they are going to use only for 300 seconds for a laying up of single layer. But still we are saying always a problem with time. Is there any other alternative way, or you can any other way you can build up the speed of the material, speed of the equipment, or speed of the product development? One, it's quite common way, that is increasing the layer thickness, but once we cannot go behind a particular limit because layer thickness may add up with, or it can embed, or it can curl, or it can leave wavy output, many other problems. Is there any other way do you think we can achieve? Scanning speed, that's again a critical parameter. We cannot go behind a particular speed, because once the scanning speed we are keep on increasing, again it need a minimum time to interact with the material. We cannot attain a monomer conversion to polymer conversion which in a very short time. So we can have it by varying the scanning velocity. That depends upon what kind of material or what kind of resin we are using, as well what kind of output we require. We cannot achieve 100% quality product with any of the methods, because we may leads to have a number of problems associated with scanning speed as well. Is there any other alternative way do you think? We can assume that we are improving the material property, but still is there any other way by playing around these parameters? Intensity of laser, okay, again the problem is once the intensity is more or less, it leads to variation in the curing depth. That's what we discussed already. Is there any other alternative? How do we achieve, or how this can be processed in another way to achieve it? It's very simple. Say for example, here I said one int in the starting itself. We can achieve it by scanning it in either way, or even back and forward. Once we can keep on changing or alternating the layupping from different directions, there may be possibilities of increasing the speed and increasing the quality as well. You can say for example, you can lay from forward to backward, backward to forward, front to back, and back to front. So there may be problems as well, but preferably if you have the capability to play around by different layering techniques, that is different methods of scanning, you can achieve. That is one of the technique they have followed, and they have achieved some of the problems. They have overcome some of the problems, like they can increase the speed of the material as well, so production rate they can increase, and as well as they can avoid particularly curls and embedding effect in the product at the middle surface, but they had a problem with end surface. Edge there is a problem, but in the middle they have achieved 100% accuracy. So likewise we should, particularly if you do any research based on this particular area, particularly additive manufacturing, only you should focus on parameters always. That's why I would like to stress more on parameters instead of process, advantage, disadvantage. In this session we have discussed about stereolithography process, modes and variants has been discussed, along with the process parameters related with stereolithography has been addressed in detail. Students can note down these questions related to the session which we have discussed. Discuss in detail about the SLA process with the different modes and with the different variants. Explain in detail about the SLA process parameters.
My question is about velocity of laser and exposure times. Okay. There are some applications, exhaust manifold. clamping areas are needed some additional hardness. Can I control that particular area, the laser? By controlling that particular area, could we enhance the property of that? That's what question.
Okay. So we even discussed this same in little different manner in last week as well. So what actually we can do is, if you need to have the control mechanism for the entire input, then we can increase that particular point more exposure or less exposure. Again, it's like if you are leaving it for a single go, say for example, if I need a constant input throughout, that's easy to achieve. If I need to play, again, all the parameters we need to optimize based on that, and again it's little complex, or the cost of the machine goes higher, because each and every time I need to change the input parameter as well. And also I have input from the CAD file, it doesn't know where we need to give more input or more we need to, but that we need to optimize. Even sometimes we need to optimize in STL file conversion itself. This particular parameter we need to have a higher exposure or higher input. That's again, it's not a simple way to achieve it, but we can try.
Not every polymer will respond to the wavelength of light which we are using, laser light. If you are using the same laser for all the materials,
Okay.
every material will not going to respond in the similar way for a particular wavelength. So we need to have change in laser for different materials.
Okay. We may not have, even as I said, some machines they are manufacturing based on the product. Even the SLA machine itself, I have studied somewhere, so they are manufacturing the entire product based on the output parameter, because we cannot say all the laser input may give same conversion rate or the monomer to polymer rate. Even there may be a minor change in the rate, conversion rate, or the polymerization process, that again leads to not a quality product. There may be some defects always. So we should optimize. That's why we were discussing in those parameters in detail in optimization. So we need to optimize. Based on that only we can able to attain a desired output, whatever it may be. The material, based on the material we need to rethink, or based on the material we need to optimize the input to achieve a better quality. We don't have any other option. If we are, as we said, if we keep on changing the product, for sure we cannot get that. Thank you.